and, or, and not functions. And is an operation. It's a mathematical operation that works with binary digits. So it works with bits. Binary digit is really the name of a digit that is either on or off, and that it's shortened to bit, the first part of binary and then the last part of digit. But you can take these numbers, and if you restrict yourself to these numbers 0 and 1, then there are other operations that are useful in using these things. So an AND gate, for example, is just a function that implements the AND function. And the idea behind an AND gate is if A and B are on, then the result is true, or the output is on. And so we can write what's called a truth table. If you look on the lower left corner of the screen, you see an AND truth table. It shows you all the possible combinations of inputs A and B and what the output is for each combination. Now remember, A and B can't be a half, they can't be 2, they can't be negative anything, right? So it's either 0 or it's 1, and so it's easy to write out all the different possible combinations of the variables A and B. And the only time that the result of an AND function is 1 is when both A and B are 1. So if we were to lay out 4 different AND gates, and this is the symbol for an AND gate, and look at all the different possible combinations, the only gate that would have an output that is on is the one that has 2 inputs that are on. In terms of switches, the AND function looks like 2 switches in series. So you notice we've got switch A and switch B. The only time the output, or the light, is on is when switch A and switch B are closed. So switch A has to be true and switch B has to be true. In other words, they both have to be closed for the output to be true or on. An OR gate is a little bit different. An OR gate has a different symbol, and the mathematical operation, the way we define this, is different. It is that if A or B is on, then the output will be on. So you notice in the truth table that the only time the output is off is when both inputs are off. Otherwise, one of the inputs is on, so the output is on. If we lay out 4 OR gates and look at all the possible combinations 0, 0, 0, 1, 1, 0, 1, 1, then we notice that the only time the output is off is when both inputs are off. So in other words, if input A is on or if input B is on, then the output is on, or in other words, the output is true. This is analogous to 2 switches that are in parallel with one another, where we're trying to turn on the output, we're trying to turn on the light, and so we can either turn on switch A or we can turn on switch B, and the light will come on. The NOT function is an inversion function. Now it only has one input, whereas OR and AND both have at least 2. It turns out you can have more than 2 inputs to an AND gate, and an OR gate can accept more than 2 inputs as well, but 2 is pretty common. For a NOT gate, it can only accept 1 input, and all it does is inverse. It gives you the opposite of what goes in. So if the input is on, then the output is off. If the input is off, the output is on. So it's a NOT. It's not whatever it was. It's the other thing now. Now, it's not really the triangle piece that indicates the inversion function, the NOT function. It's really that little circle on the end. In electronics terminology, that triangle is normally recognized as a buffer or an amplifier, something that's making sure the signal is not degraded as it traverses over, maybe a distance or something. It's the circle itself that represents the inverse, or the thing that gives you the opposite of whatever you had. So if you put in A, I don't care if A is 1 or 0, on or off, I will give you the result, or the reverse of that, the opposite of it, out. The NOT function is kind of like a normally closed switch, where if you don't press the button, then the light is on, but if you do press the button, then the light is off. Now we have to be careful here, because a switch really doesn't have, or a button doesn't really have a passing power or not passing power state. It's the switch associated with the button that determines that. A lot of push buttons are normally closed buttons, and so when you push the button, in other words, when you activate the button, it breaks the contact, and that's what we're talking about here. But there are many more buttons where when you press the button, it makes the contacts. In other words, it closes the switch, and that would be a normally open type. So in the terminology of buttons, let's refer to them as active, in other words, pressed, or inactive, and then the switch associated with them may be normally open or normally closed. The NOT function can be used with the AND function. In fact, all of these gates, since their inputs are binary signals and their outputs are binary signals, they can be tied together any way you like. As a matter of fact, you can make some very useful things with these. This is how all computers actually work, including your smartphone, your smartwatch, whatever you have. If it has a microprocessor, it's using gates and it's using binary digits. So it's important to understand them and how they work, because further this will help us in ladder logic programming. So if we consider a system set up as you see here with an inversion first driving one leg of an AND gate, then could this be a useful circuit? Well, this is a circuit for a particular device, and you'll notice that A represents power being on. When we turn on the power, then that leg is true. On the other hand, B represents the pressure switch being open. Okay, so when the pressure switch is open, in other words, when the pressure is not too high, or when the pressure is low, when the pressure switch is open, then the inverse of that is a true. Okay, so you notice what's coming into the AND gate is a true, the power is on, and the pressure is too low. So a low pressure indicator can turn on, right? So why would you have a low pressure indicator on if there was no power to the device, if there's no way the compressor can do anything about it? You wouldn't, right? So you would need this logic to determine when to turn on an indicator to the user to say that, hey, the power's on, but the pressure's still too low to be useful. Okay. On the other hand, if the power was on and the pressure switch was closed, well, the inverse of true, B, is false, 0, going into the AND gate, and so A being 1, in other words, power is on, and the inverse of the pressure switch closed, the 0, 1 and 0 is 0, therefore the low pressure indicator light would be off. And you can write a truth table for this. You see that the two inputs are the pressure switch and the power indicator, and you can see what the pressure indicator should be in each of the possible combinations. Now, it would be possible, of course, to consider the case where the power was off and the pressure switch was either on or off. But obviously, if the power is off, then the pressure indicator is going to be off because A will be a 0. Now, it turns out it's actually easier to make what's called a NAND function in circuitry. So a not AND. In other words, AND A with B and then invert the result and output it. Turns out I think it takes 1 or 2 less transistors, something like that. It doesn't matter. The point is that it's fairly common. And notice that what it is, it's the opposite of AND. So A and B, if we take 0 and 0 is 0, inverse of that is 1, so there's our first row in the truth table. 0 and 1 is 0, inverse of that is 1. 1 and 0 is 0, the inverse of that is 1. 1 and 1 is 1, the inverse of that is 0. Now this may sound a lot like the OR function, because you remember with the OR function, 3 were on and 1 was off, but it was the opposite way to this. With the OR function, 0 or 0 was 0. It was 1, let's see, the rest of them were either 0 or 1, 1 or 0, 1 or 1, and you got 1. So our 0 would be at the top here on our output Y. Whereas the NAND is a different function than OR, and it's a different function than AND. It's the inverse of AND. Now you can buy these in gates. You can buy these in chips. There's a little schematic off to the right that shows you the pinout of a quad input, there's 2 of them, NAND gate chip. So there are 4 different inputs on pins 2, 3, 4, and 5, for example, on the left-hand gate, and then the output is on pin 1. The gate on the right-hand side, you can see the numbers associated with it. Pin 6 and pin 8 have no connection, and then you have to supply this with power and ground, of course, for it to operate. You have to give it electricity. But you can buy these chips. These are available things. They're not particularly expensive now either. The NOR function is the inverse of OR, and so what it does is you take the OR of A with B and then invert it. So 0 or 0 is 0, the inverse of that is 1. You see Y is 1 on the first row there. 0 or 1 is 1, the inverse of that is 0. And so for the rest of the table there, you notice that the output is 0 because one of the inputs are on. On the right hand side, I've got a little schematic picture of a 2-input quad NOR gate chip. So there's 4 NOR gates in this thing, and there's 2 inputs to each NOR gate. And you can see the pins there and how they're laid out. And I've included a picture of what this would look like essentially. Most of these logic chips look like this. These are not as common anymore as they once were. Today you can get a whole lot of gates in a really small package, and you can actually wire them together internally by programming. And those are called programmable logic devices. And for the price you'd pay, even though these are cheap, the price you'd pay for 10 or 20 of these, you could get one PLD device, programmable logic device, and use it instead, and have a whole lot more gates and be able to do a lot more interesting functions. Exclusive OR is a little bit different than OR. It looks like OR at first because we've got 0 or 0 is 0, 0 or 1 is 1, 1 or 0 is 1. But then 1 exclusive OR with 1 is 0. So the exclusive OR function matches OR all the way up to the point where we have 1 or 1. You'll notice the symbol is a little bit different. It looks like an OR gate, but it's got an extra line on the back. And what this really does is allow us to compare two binary numbers. Notice that when the two numbers are the same, we get a 0, but when the two binary numbers are different, we get a 1. So 0 or 1, or the alternate case 1 or 0, both give us 1s, whereas 0, 0 gives us 0, 1, 1 gives us 1.